All right, good morning. So here we are again for another lovely session of MENG 3310 Fluid Mechanics. This will be the 20th lecture in the series, and we're going to be discussing some things from chapter 6 of the text, covering acceleration fields, velocity fields, finishing up with the continuity equation, etc. In the next lesson, we will be moving on a bit to dimensionality and similitude and some other things. Although, depending on the time we have, I may have to put something else together to finish up this material, but we'll get it together. So, okay, without further ado, let us begin. So what I want to do today is remind us of some of the equations, and then also go and work through a few examples of applying these equations from chapter 6 of the text. So, first of all, we've seen fields before, things like acceleration, velocity fields, etc. So I just want to remind us of the definition of an acceleration field. So an acceleration field will be something like this, where you have, well, obviously, I know that my acceleration vector for a field is going to be equal to dv dt, is going to be equal to dv dt plus u dv dt, partial of v with respect to x, I should say, plus the partial of v with respect to x, plus the partial, plus v times the partial of u with respect to y, or sorry, partial of v with respect to y, partial of v with respect to y, plus w times the partial of v with respect to z, where the velocity vector v is equal to simply the x, y, z components, ui plus vj plus wk. Our velocity, we have our velocity field, and then our velocity at a point, and then also our acceleration field. So we know, or this is just our velocity vector, I should say. But then if we break this down to look at a field at a point, I could say the x component, ax, is the partial of u with respect to t, plus u times the partial of u with respect to x, plus v times the partial of u with respect to y, partial of u with respect to y, plus w times the partial of u with respect to z. So just reviewing through a few equations here. And a y is equal to the partial of v with respect to t, plus u times the partial of v with respect to x. That was a really bad x right there. With respect to x, plus v times the partial of v with respect to y, plus w times the partial of v with respect to w. And then az, with respect to z, helps if I write the right variables. And then az is going to be equal to the partial of w with respect to time, plus u times the partial of w with respect to x, plus v times the partial of w with respect to y, plus w times the partial of w with respect to z. And all of this feeds into the rotation, the acceleration vector.
dv w
On y. Oh, did I put the wrong thing on there?
w dv on y. No, ay.
Ay here? What did I
That's over, yeah.
Possible. I wrote something down wrong. W times the partial of v. Sorry about that, yes. Too many variables to not make typos. Okay. And this would be our acceleration field. Here. All right, so we can also look, so these are just a few tools that we're going to use today. So basically, I'm just going through a few of the equations that we're going to use, and then I'm going to work through some examples of these equations. So you can find these in your book as well. And our rotation vector, if I look at the rotation vector W, the rotation vector is W, the W vector, and W is equal to 1/2 times the partial of W with respect to Y, the partial of W with respect to Y, minus the partial of V with respect to Z, all of this times I, sort of a cross product thing going on here, plus the partial of U with respect to Z, minus the partial of W with respect to X, times J. So this should look very familiar in sort of as a cross product you might have. Or you might remember from your earlier courses, times the partial of V with respect to X, minus the partial of O, minus the partial of U with respect to Y, times K. And then we would have this 1/2 would be multiplied times the entire thing. And then the individual components of this, the x, y, z components of the rotation vector. Actually, I should probably maybe call this omega even instead of, maybe I want to call this omega instead of w to not confuse these. So omega x would be 1/2 the partial of w with respect to x minus the partial of w with respect to y, or the partial of u with respect to y here. And then here, actually that should be a y here, I believe. No, actually that's okay, sorry. X and omega y is equal to 1/2 times the partial of u with respect to z minus the partial of w with respect to x, partial of w with respect to x, and omega z is equal to 1/2 times the partial of v with respect to x minus the partial of u with respect to y, minus the partial of u with respect to y here. And this one isn't quite right. This should be probably w. What is that one? That is, I want to say it's, I have it in my notes with respect to x, but that probably should be perhaps, I would need to check that. Can anyone have their textbook handy? Okay.
Isn't it just following the top?
Yeah, it should actually probably be y. You're right. Sorry about that.
WY
Yeah.
minus
dz. I need to double check that. So, yeah, let's do dv dz. Yeah, that would make sense. That would follow our pattern. Sorry about that. A little error in my notes here. Okay. And these are equations 6.13, 6.14, and 6.12 in the text. Helps if I have my notes proper. All right. So a few things, and then also we also need to reference the continuity equation. So again, I'm just sort of relisting our list of tools that we can use through some of our analysis problems that I'll be working through. I also look at the continuity equation. I can also look at the continuity equation. Which states here the partial of rho with respect to time, that's rho density, plus the partial of rho u with respect to x, plus the partial of rho v with respect to y, plus the partial of rho w with respect to z. All of this is equal to 0. So rotation vector omega all of this is equal to 0. And again, this is just based off of conservation of mass flow, volume flow, etc. Okay, so let's actually see an example of this, how we might start working through some of these, how we might actually make some sense of this. Okay. So consider something like this. For an incompressible flow, which means rho will be constant, I am told that u, so basically the u, that is the velocity in the x direction, is a function of x, y, and z, where u is x squared plus y squared plus z squared. And also, v is equal to xy plus yz plus z. And w is unknown. And I wish to determine w. Determine w required to satisfy a continuity equation. Required to satisfy the continuity equation. Yes, sorry, that's pardon my bad handwriting, that is a question mark, yes. The continuity equation. So basically, I am saying that we have a x velocity as a function of x, y, z, a v velocity, or sorry, y velocity as a function of x, y, z, and I want to see how these relate in using the continuity equation to find what the vertical or the w velocity component must be. So I'm going to assume steady state. So solution here. So it is not stated, so we don't know anything about time, so I'm going to assume steady state, so the partial with respect to time will be 0. So our continuity equation will come to well, the partial of u with respect to x plus the partial of v with respect to y plus the partial of w with respect to z all must be equal to 0. All right, so let's work through that. So this is just a restatement of the previously mentioned or previously written continuity equation, and we're going to use this differentiation and integration in order to find the w expression. Okay. Any questions on what we're going to be doing? So again, this is going to be a fairly simple, fairly straightforward application of the continuity equation and its differential and integral relationships. So in other words, if I substitute these terms in, the partial with respect to x of my x equation, which was x squared plus y squared plus z squared, plus the partial with respect to y of xy plus yz plus z plus the partial of w with respect to z, well, all of this must be equal to 0. So again, I'm taking these terms, and I'm going to take the derivative with respect to x of this thing, the derivative with respect to, or the partial with respect to y of this thing, and then I'm just saying we'll solve for this, and then we'll integrate with respect to z, and we'll be able to get the w function, at least in the general form. So if we do this, we get that the partial with respect to w. So if you go through and take the derivative of this with respect to x and take the derivative of this with respect to y, the partial, I should keep saying derivative, I should say the partial of this with respect to x, the partial derivative of this with respect to y, you will get that the partial of w with respect to z is equal to negative 2x minus x plus z. or this is equal to negative 3x minus z. And so finally, if you integrate with respect to z, with respect to z, if I integrate this with respect to z, I will get that w is equal to negative 3xz minus z squared over 2 minus z squared over 2 plus c. And I will say that c has to be a function of x and y. It could actually be a function itself, but it has, or an expression itself, but it has to be some sort of expression of x and y. Because this is basically just your constant integration, but I will mention that it doesn't actually have to be a number like 1, 2, 3, 5, a real number, whatever. It could actually be you could have like x squared y or something like that. The only requirement is that when you take the derivative of it, it goes away. Or sorry, when you take the partial derivative of it with respect to w, or sorry, with respect to z, it goes away. So, for example, so this would be my final reported answer. For example, one possibility would be something like w equals negative 3xz minus z squared over 2 plus, I don't know, 2x squared y squared. And don't be asking where I got that. I just pulled that constant term, I just pulled it out of my head. It could be any expression of x and y. It was just something that popped into my head. It could be 3x squared y. It could be x squared y to the 4th. It could be x squared plus y squared. It could be any function you want, as long as it's only a function of x and y. If I actually wanted to find the full expression, I would need a specific solution or a point or some more information about the system other than just the constant. Any questions on that? Again, I think this is a fairly straightforward application of our continuity equation. Okay. So next, I want to look at the stream function, which is when we're looking at the stream function, we're going to be collapsing the continuity equation to 2 dimensions, or reducing things to 2 dimensions. Let's reduce this thing to 2 dimensions. So again, we have our continuity equation, which is our partial of rho with respect to t, plus the partial of rho u with respect to x, plus the partial of rho v with respect to y, plus the partial of rho w with respect to z, equals 0. Now, if I have a steady, so let's look at this, continuity for steady, incompressible 2D flow, so what if we look at so basically I'm saying, what if we look at a 2-dimensional system? Well, because it's steady and incompressible, I can say the partial of rho with respect to time is going to be equal to 0. So that's just 0, because again, the only way it will be compressible is if obviously the density is changing in some way. That's the very definition of incompressible. And of course we know from our early discussions that water isn't perfectly incompressible, but most fluids, water, oil, can be reasonably modeled as incompressible, so that's a good thing. And also we can say the partial of, so if we look at it, if we are interested only in a 2D flow, we can say the partial of rho w with respect to z is also equal to 0, because this is the 2D system. So we're looking at only the x and y. So then I would have the continuity equation would then collapse to the partial of u with respect to x plus the partial of v with respect to y is equal to 0. So this is the continuity equation in 2D. Well, 2D incompressible steady state. You could also have, you actually could have a incompressible, you could actually have a change in rho even with an incompressible flow, but only if it wasn't steady state. So you had like more than one fluid in a system, like maybe you had like a mixture of oil and water or something really weird like that, where you actually had two different fluids present, or you'd have to get a really exotic system, something like that. But I suppose we could torture it until we got something like that. Okay, so I want to move along to define a function that I'm going to call Sigh, the Greek letter Sigh. So I'm going to define a function, so I'll call this Sigh. Sigh. And that's spelled P-S-I-E. That's not the Sigh, the S-C-Y, which is the mascot of the Iowa State Cyclones. But anyway, that's neither here nor there. So what this is going to be is, sorry, that's a very obscure reference for Texas, not an obscure reference for Iowa. But anyway, where this is, u is going to be equal to the partial of psi with respect to y, and v is equal to the negative partial of psi with respect to x. So that this satisfies continuity. So this satisfies u, actually the partial of u with respect to x. Or should I say, so this satisfies the partial of u with respect to x plus the partial of v with respect to y is equal to the partial of, with respect to x, of the partial of psi with respect to y plus the partial of y, or sorry, the partial with respect to y of the negative partial of psi with respect to x. With respect to x, all of this equals 0. And the whole reason for this, the whole purpose for this, is that if we have u and v, if we find this function, so we start off with u and v, which are two functions, we can then collapse these further using streamlines. So using the stream function, down into psi, which will be one function. And this will ensure that the conservation of mass is satisfied. All right, so so that may seem like Greek right now. Actually, definitely Greek with the psi in there. But let's see how we might work through this. I'd like to work through an example of finding the psi function. All right, so example 2. The velocity components of a steady state, of a steady incompressible a steady, incompressible, two-dimensional flow 2D flow R, so this is given. U equals 2y, and V equals 4x. So again, back to basics. If at our coordinate system, if y equals 2, then we'll have a x velocity of 4. If x equals 5, then we will have a v velocity of 20, etc. And so we can also see from this that the x velocity does not change as we move along the x-coordinate, and the y velocity does not change as we move along the x-coordinate. They're constant in their own axes. So this is given. And find, determine the corresponding stream functions or function, I should say. And so basically determine the corresponding stream function. Basically, that's all we really want to do. Determine the corresponding stream function. So, u, which must be equal to the partial of partial of psi with respect to y, is equal to 2y. And v, which is equal to the negative partial of psi with respect to x, is equal to 4x. Then psi this. So from this, I can get, if I integrate this with, basically if I bring this over here, bring the partial of y over here, integrate both sides, I can get that psi must be equal to y squared. Y squared, so just integrating with respect to y, plus some f1, some constant function, essentially, some function of x. And then from here, I can say that psi must be equal to negative 2x squared plus some function of y, some sort of function of y. And, or in other words, psi must be equal to, and so, you know what, there's no reason we can't just say, oh, let's just let this and this be our constants when combined together. So psi can just be treated as the summation of these two, negative 2x squared plus y squared, and then there would be some sort of actual numerical constant c. So the function for y, for the x here will be this x over here function, and the y component of the function will be this y here, and then you would have some sort of numerical constant. And so then we have this. We can say, for simplicity, let c equals 0. Although if we had more information, we could actually solve for the c directly. For simplicity, if I can spell simplicity correctly. Set c equal 1, or set c equals 0. So then I would have that y squared over psi minus x squared over psi over 2 equals 1, our constants here. Or simply psi is equal to negative 2x squared plus y squared. Psi equals negative 2x squared plus y squared. And now I have collapsed this function into one general relationship here. All right, questions on that? Okay. So there is that. I do have another lesson I need to do eventually on stress deformation relationships before we really get into including the Navier-Stokes equation, before we get into dimensionality and similitude, but I may record that for Friday or something. So, okay, I think that'll do it for today. If you have any questions, feel free to see me during office hours, but that will finish up our brief lecture for today. As always, thank you.